Question 6.2. We are given this reaction at equilibrium, and we are given the equilibrium constant values at 3 different temperatures. First, we need to state whether the reaction is endo or exothermic. And in the next question, we need to give an explanation. Now, the equilibrium constant, Kc, is only dependent on temperature and changes according to the temperature. For the given reaction, we can see from the values in the table that increasing the temperature causes an increase in the value of the equilibrium constant. The equilibrium constant in general is the ratio of the concentrations or pressures of the products over the concentrations or pressures of the reactants. The value of Kc increases if the numerator value gets larger, that is, the concentration or pressure of products increases. Or Kc can increase if the denominator value gets smaller, that is, the reactant concentrations or pressures decreases. Another way of putting this is that if the forward reaction is favored, then Kc increases. Since the Kc values get larger with increasing temperature, and since endothermic reactions are favored by an increase in temperature, this tells us that the forward reaction is endothermic. We must note, however, that for the given reaction, the reactant is a solid and so is not included in the equilibrium constant expression. Only the products are included since they are gases. Lastly, we must calculate the mass of the reactant, ammonium hydrogen sulfide, that exists at equilibrium when the temperature is 250 degrees Celsius. Whenever we need an equilibrium quantity of a substance, we probably will be needing a Rice table, where R is the reaction and stoichiometric ratio, which is 1:1:1. I is the initial moles of species present in the vessel. C is the changed moles, that is the moles of reactant used up, and the moles of product formed, and E is the equilibrium moles. We are told at the beginning of the question that the volume of the vessel is 3 decimeters cubed, and that the mass of the reactant put into the vessel was 70 grams. We can convert this mass of the reactant to an initial mole value by dividing its mass by its molar mass. And we need information from the periodic table to calculate the molar mass. We get 1.37 moles of reactant present in the vessel initially. We can fill this value in on the table, and initially there are 0 moles of each product present. Then the reaction starts. We don't know how many moles of reactant are used up, but we can call it X moles, and we put a minus sign in front as it is used up. Then, since the ratio of reactant to each product is 1:1, we can say that X moles of each product form, and they will have plus signs since they are forming. So at equilibrium, the moles of reactant present is the moles initially minus the moles used up, so we get 1.37 minus X. And the moles of each product at equilibrium will be the moles of each formed, which is X. We now have the moles of the reactant present at equilibrium in terms of X, but we want the mass present at equilibrium. So we first need to solve for X to get an actual mole value at equilibrium, and then we can convert that mole value to a mass value. We can take the equilibrium constant expression and substitute the equilibrium constant value at 250 degrees Celsius, which is 18 times 10 to the minus 2. And then, using the formula concentration as moles divided by volume, we can put in the concentration of each product. And how we do this is we take its moles, which is X, divided by the volume of the vessel, which is 3 decimeters cubed, for each product. Simplifying and solving for X, we get 1.27 moles of each product present at equilibrium. But we want the moles of reactant present at equilibrium, and so we take its value in terms of X, substitute the value of X, and we get 0.1 moles of reactant present at equilibrium. Then the mass of the reactant at equilibrium is its moles times its molar mass, which gives 5.01 grams of ammonium hydrogen sulfide at equilibrium at 250 degrees Celsius.